The nature of space-time. As people of Earth, we take space for granted. From our perspective, it's a zone that occurs about 100 kilometers above the planet, where there is no air to breathe or scatter light. It's just emptiness after that, right? Time also ticks on incessantly. Well, it's not that simple. One thing that physicists have learned over the past century is that space and time form a system of such staggering complexity that it might defy our understanding of reality. So let's take a look at what space-time is composed of in this video. Space is really big, and also we don't know much about the properties of space-time itself. We know it warps and curves, but what exactly is it made up of? Astronomers have worked out only 5% of the universe, which consists of baryonic particles. The rest, 95%, is dark matter and dark energy. We still don't know anything about them apart from observing their effects. Space seems empty to us, but that is not the case. The observable universe is 46.5 billion light years in diameter. The age of our universe is 13.8 billion light years. We know all this by observing all the light coming from the distant galaxies reaching as far as the Big Bang. The cosmic microwave background radiation is the afterglow of the Big Bang, which tells us about the early universe. Further, space is a vacuum, but that doesn't mean it's empty. Gas, interstellar dust, and other bits of matter float around in the emptier areas of our universe, while the more crowded regions host planets, stars, and galaxies. However, we cannot be sure that our universe is the only one that exists. We don't know what exists beyond the observable universe. But what is dark energy? What is this mysterious force that makes up about 68% of our entire universe? In the early 20th century, scientists were sure that the expansion of the universe had to slow down over years. They thought so because the energy density would decrease and gravity would dominate, causing the expansion to slow down. Just like you throw a ball up in the air and it comes down after a period of time. But when Hubble turned his telescopes toward the sky in 1929, he observed that distant galaxies were moving far away from one another. He then gave the famous Hubble law. According to it, every distant galaxy is moving away from each other with a velocity proportional to its distance. The farther away a galaxy is, the greater is the velocity with which it moves away. This idea was baffling for everyone. It's just like throwing the ball up in the air, and instead of slowing down and coming back to the Earth, it keeps speeding up and moving away from us, eventually in space and away. If we observe something like this with the ball, we would assume there's an invisible force behind it. Astronomers called it dark energy, discovered by mainly three scientists: Adam Rees, Saul Perlmutter, and Australian astronomer Brian Schmidt, who won the Nobel Prize in 2011 for their discovery. It is the most important discovery in the history of science. Discovering the dark energy and that it's causing the universe to expand at a faster rate was shocking for scientists. We've estimated the rate of acceleration by using the Planck telescope to map the cosmic background radiation left over by the Big Bang. Final data released by the Planck mission last month reaffirmed that dark matter and dark energy must exist, even if we don't know what they are. In a few hundreds of billions of years, everything but our nearest neighboring galaxies will have moved out of reach. No matter how fast future humans might travel, we'll never be able to reach anything else. More about dark energy is unknown than is known. We know how much dark energy there is because we know how it affects the universe's expansion. Other than that, it's a complete mystery. One explanation for dark energy is that it is a property of space. Albert Einstein was the first person to realize that empty space is not nothing. Science has amazing properties, many of which are just beginning to be understood. People think that space might even be infinite. But what is in this space? Apart from planets, stars, comets, asteroids, dust, and black holes, and some other objects, almost everything out there is hydrogen. Hydrogen is everywhere. It's the lightest element to exist. It can be found anywhere from hot, dense stellar nurseries to the cold and empty voids between the galaxies. As Harlan Ellison wittingly said, the two most common things in the universe are hydrogen and stupidity. Hydrogen is the most abundant element in our universe, but what about the space between hydrogen atoms? What is a vacuum of space made up of? This is where I would have to call quantum mechanics and things get really weird. Richard Feynman said, "I think I can safely say that nobody understands quantum mechanics." And that's very true. On the very smallest scales, it appears there is a minimum resolution to the universe called the Planck length. On these scales, the universe appears to be a strange quantum foam, with virtual particles popping in and out of existence obeying the laws of quantum mechanics. No matter how counterintuitive this sounds, we can actually measure the effects of quantum mechanics in the laboratory. For example, the Casimir effect. If you place two very thin plates just nanometers apart in a vacuum, classical physics might tell you that the space between them is empty. But the sea of virtual particles predicted by quantum physics is affected by the boundary of the plates. Fewer virtual particles can be created in this small confined space than on the outside of the plates. This vacuum energy might actually be the key to understanding dark energy of the universe on the largest of scales. Quantum mechanics is our deepest, most comprehensive way of understanding reality. But the problem arises when trying to understand quantum mechanics. Honest physicists admit that we don't truly understand quantum mechanics. We have a recipe that we are taught in our textbooks, but we don't exactly know what's going on behind the scenes. But the mysteries of quantum mechanics are a topic for another video. That was all about space and what it is composed of. What is space-time? Space and time are like the opposite sides of the same coin. The famous physicist Albert Einstein had developed the idea of space-time when he unified these concepts in the theory of relativity. In simple terms, we all know about the three dimensions of our 3D world: length, width, and height. Einstein united it with the fourth dimension, that is time. We can stay at rest in space. For example, a man sitting at rest on his chair. But we always move through time in one direction. It never stops. According to our current understanding of physics, space-time explains the unusual relativistic events that arise from traveling near the speed of light and the motion of massive objects in our universe. Before Einstein had united space and time, Newton's laws described the motion of massive objects, while Maxwell's equations described the properties of light. But by the end of the 19th century, there was something special about light that was bugging every physicist. Experiments showed that the speed of light was always constant no matter from which reference frame you observe. Around the same time, French physicist Poincare speculated that the velocity of light might be an unsurpassable limit. Ultimately, Einstein pulled all of these ideas together in his 1905 theory of special relativity, which postulated that the speed of light was constant. For this to be true, space and time had to be combined in a single framework that conspired to keep the velocity of light the same for all observers. Einstein, though, didn't reach the conclusion himself. The idea that space-time is a single fabric came from German mathematician Hermann Minkowski in 1908, who said, "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." The space-time described by him is known as the Minkowski space-time, which serves as the backdrop of calculations in both quantum field theory and relativity. But how does space-time work? Today, whenever people talk about space-time, they often describe it as a sheet of rubber or, more often, a fabric. This comes from Einstein, who realized as he developed his theory of general relativity that gravity was due to warps and curves in the fabric of space-time. Massive objects like the Sun and Earth create distortions in space-time that cause it to bend. These bends or curves constrict the ways in which everything moves in the universe, because objects have to follow the path along the curved space-time's curvature. Motion because of gravity is actually motion along the curved space-time. NASA actually sent a mission called Gravity Probe B, which measured the shape of the space-time vortex around the Earth in 2011, and found that it closely accords with Einstein's prediction. But still, much of it remains difficult for people to wrap their head around. Though we can discuss space-time as being similar to a sheet of rubber, the analogy eventually breaks down. This is because the rubber sheet is two-dimensional, whereas space-time is four-dimensional. The warp is not just in space, but also in time. Despite its intricacy, relativity remains the best explanation for the physical phenomenon we observe. Yet there is a problem looming over the horizon for physicists over the past 100 years. As discussed above, the problem is to combine general relativity with quantum mechanics, which explains the properties of subatomic particles with extreme precision but does not incorporate gravity. Some theorists speculate that space-time itself comes in quantized chunks. Some are trying to quantize gravity. Traditionally, when people talked about quantum gravity, they were referring to quantum discreteness, quantum fluctuations, and almost every other quantum effect in the book. We hope this problem might be solved in the future by our scientists. But one thing that all scientists agree on is that empty space is surprisingly complicated. What do you think about space-time? Can you try visualizing it? Let us know your thoughts and questions in the comment section below. And don't forget to like the video and subscribe to our channel, and press the bell icon to remain notified of future amazing videos like this.